In this episode, I have the extreme pleasure of speaking with Emanuele Rossi, who's a machine learning researcher at Twitter and a PhD student in Michael Bronstein's lab. We cover quite a bit of ground in the interview, but our main focus is on his Scalable Inception Graph Neural Networks paper. And this is mainly around addressing the issue of internet scale graphs and how we can apply these GNN methods to them. And through that paper, there's a lot of discussion around graph-based operators, and it gets to the fundamentals of these approaches, and I think it's super enlightening. We also talk about the challenges of applying GNN-based methods to these industrial scale problems. So I learned a lot from it. I hope you will as well. Before we get there, let me mention I do have a mailing list where I send out updates of content I release across a variety of platforms, as well as a Discord server and a Patreon. And I'll have links to all of those things in the description below. Thanks. Emanuele, thank you for joining. This is awesome to have you. Really excited for the conversation. I've been reading a lot of your work and just super excited. So thanks for taking the time out of your day. I'm sure you're a busy guy.
Thanks for having me.
Yeah, so can you just start by telling us a little bit about you and how you came to be doing research on graphs with someone like Michael Bronstein and working at Twitter and all that stuff?
Yeah, sure. Yeah, I think basically it kind of all started. I was doing my undergrad was in computer science at Imperial College, and in my second year, I basically did an internship at Google in that quarter in Mountain View, but on completely different stuff. So I was working on software engineering, and but there I met another intern, was Federico Monti, and then we became very good friends. And then he started telling me what he was working on, and it turned out that he was a PhD student with Michael at the time. Working on some of the first GNN models. So this was basically 4 years ago. So it was literally I think there were like 5 papers, or not even that, on the topic. And but yeah, I was pretty excited. I was pretty excited about that. So basically, then I when I went back to Imperial, I started studying a bit more about machine learning. Started getting involved with some projects with Federico and Michael, and then I did my master's in Cambridge, but I kept also in touch with them. So also in Cambridge there is a group that works a lot on graphs, where Peter was, and so I worked. My supervisor for my master thesis was Pietro Liò, who was also Peter's supervisor. And also basically Michael co-supervised my thesis. So we kept in touch, and my work there was, GNN, but more for applied to biological data, in particular RNA. And yeah, from there, basically we liked a lot working together, and they started Fabula, the startup basically working on fake news detection using graph neural networks. And yeah, still during my master's, I joined them part-time, and very soon later, it was acquired by Twitter. So we were all very excited to join Twitter. So then we basically formed a new team inside Twitter, focusing on both kind of research, fundamental research, and some more applied problems around GNNs. And yeah, so we've been inside Twitter for basically a year and a half. And yeah, and now in October, I've also managed to start a PhD inside Twitter, and in collaboration with Imperial, with also Michael as supervisor.
Wow, you sound really busy, but also like you've been doing a lot of exciting work. So you mentioned the fake news detection from Fabula. Are you still working on that problem mainly within Twitter, or has it expanded to a more general problem set that these methods are working well for?
Yeah, no, we work on a lot of different topics. So I mean, I guess the goal of our team is more in generally trying to apply graph neural networks for a variety of applications of Twitter. So I mean, fake news is one of them, but as you can imagine, there are multiple.
Sure. So are you mainly, is the output of your work predominantly publications, or do you integrate with product teams and try to actually build solutions out and put them in production and all that? Where do you lay in that?
Yeah, both. Some of our projects are more theoretical, so it's mainly, you know, the outcome is mainly pure research and publications. And then some other projects are more applied. So we collaborate with some other teams inside Twitter, and basically, try to get a model to production with their support, and to have it deployed in the app.
So one of the obvious challenges of putting these in production is scale. But
Yeah.
and we're going to talk more about that. But besides that, are there any other kind of fundamental challenges you've come across that is sort of getting over that gap between a research paper and a model in production, or is it mainly just solving the scale problem?
Yeah, it's scale, but not only theoretical scaling, but also I think the infrastructure plays a very big role. So I think when you work with graphs, you need specific infrastructure that is kind of different from if you were working with images, especially if you want to work at scale in production, have a pipeline and so on. So I think also the infrastructure is kind of a very big challenge. And then yes, I guess the difference is that normally when you do research on GNN, you have one graph that is your data, and then you have to do some prediction on it. In our case, is more like a big part of time is spent on thinking. We have potentially multiple graphs, multiple sources of data, multiple features. What do we think is the best way to actually combine them, and then what should we give as input to our model? This turns out to be sometimes a very, very hard question that you don't really often face in research when you mainly focus on benchmarks.
Right. Yeah, the real data is a lot more messy. And I do have some questions later about the different relation types and stuff and how that could fit in. But before we get there, the main paper I wanted to dig in today is one that you wrote that's targeting this scalability problem with the scalable inception graph neural networks, or the SIGN paper. Can you give us just a high-level overview of the problem it's trying to solve and the solution before we dig into the details?
Yeah, so the problem, I think, is we want to have graph neural networks that are able to operate on real-world graphs. So in the first few years of graph neural network research, I would say 99.9% of the literature was focused on some toy examples. So the super popular Cora, Sightseer, and PubMed datasets, which had few thousand nodes and few tens of thousands of edges, which were great to start with, but are not very realistic, right? So in practice, many graphs that you observe in the real world have millions of nodes, tens of millions, or billions, or if you think about the graphs we have Twitters, you're gonna have hundreds of millions of nodes and hundreds of billions of edges, right? And the first problem that you encounter is that if you take a model like GCN or like GAT, as they were first implemented, they do not even run on these big graphs, just because the way they are trained is by using the whole graph at the same time. So they keep the graph in GPU memory. Now each epoch they use the old graph, they run the GNN on the old graph, and they train on the old graph to update the parameters. And clearly you cannot store a graph with a billion edges in GPU memory. And so they don't even run. So the first question is actually, how do you make models that can run on these large graphs? And then you would like them to run very, very quickly. So in order to make them run, there has been some work previous to our paper on this idea of sampling, which is basically, if you think about non-graph machine learning, what you do is, if you have a huge data set, is always, as is it always been done, we don't train on the whole data set at the same time, but we sample batches, right? So a batch is just a sample of the whole data set, and we train maybe on 128 samples at one time, and then we throw them away, we pick another 128 and train on them. And that works perfectly. The problem with graphs is that your samples are not independent, right? So if you think about node classification, the nodes are not independent. So it's not like you can just sample node randomly. Also because you can't classify a node just based on itself, but you need kind of the graph around the node to make the prediction, because this is what GNN use, right? So the GNN want to aggregate information from the graph. And so it's not trivial, how can we subsample the graph in order to do this kind of mini batch training for GNNs. And I would say, the first work going in that direction was GraphSage, which was basically just saying, introduce this idea of neighborhood sampling. So basically saying, okay, I'm going to select 128 nodes, which I'm going to compute my loss on, and then for each one of them, completely independently, I'm going to sample their let's say 2-op neighborhood, right? So this is what a GNN needs to make a prediction about my node, is just the node of this, the neighborhood of this node. Possibly, if you have a GNN with 2 layers, you would like to have the 2-op neighborhood. Of course, in many graphs, if you go 2-op, especially in social networks and so on, the 2-op neighborhood is already almost the whole graph. So you need ways to kind of even subsample the neighborhood. So you can say, okay, I'm just going to take 50 neighbors for my node, and then for each neighbor another 50 neighbors. So you kind of have an upper bound on how many neighbors you're gonna sample. Mm-hmm. So GraphSage kind of enabled training on these large graphs. And then there's been a lot of literature on how to improve this sampling with a lot of interesting works. What we did in Sign is we actually showed a way of doing this without sampling at all. So we kind of get away from the sampling, and the way we do that is by moving the graph computation as a pre-processing, which can be done very efficiently, because you're not limited by your GPU memory, right? So you can do it efficiently on the CPU, but also you can use distributed computation like Spark, and you only need to do it once. And then your model, training time and an inference time, it just becomes an MLP, which is super fast to train. And so it turns out that this way of doing it is it's basically faster than anything else, and it works reasonably well.
So in deep learning, we often add expressivity to our networks by stacking layers deeper and deeper. I think you already kind of touched on it, but can you talk about why that's problematic with GNNs and how it affects scalability?
Yeah, I mean, it is problematic because basically, if you think about GNN as message passing, and you think about the computational graph for your GNN, if you have a 1-layer GNN, for each node, each node is only gonna receive messages from the 1-op neighbors. So you can have 50, 100, maybe 1,000 1-op neighbors, but in general, in most graphs, maybe on Twitter there are some users which if you are Obama, you have 120 million followers, but in a lot of applications, the one-up neighbor is still reasonably small. But then as you add more layers, basically this makes it possible to receive messages from farther away in the graph. And so usually, if you are able to run a GNN on the full graph, a GNN with k layers aggregates information from the k-hop neighborhood of a node. So k-hop neighborhood meaning all the nodes that you can reach with up to k, up to distance k from the original node, and you can see how this leads to an exponential explosion of the number of nodes that you have to consider. Because if I start from myself, let's say I have 100 neighbors, and then my neighbors, each of them are going to have another 100 neighbors, and then as you keep going, this number grows very quickly, and in practice possibly even more, because on average there's this famous law that on average my friends have more friends than I do, right? Because you're going to have some very popular user in your network, in your neighborhood, and so yeah, you have this exponential explosion, and which makes the computation quite infeasible.
Yeah. Then I guess on the other hand, maybe you can talk just a second about the oversmoothing thing, and if you are basically having to get the whole graph as input for messages, then all the features are sort of becoming the same.
Yeah, exactly. I mean, basically, yeah. I mean, GNNs in general, especially on node classification, they tend to work well because they do some sort of smoothing. So what you would like to do if you do a one layer GNN, you're basically saying something like, my features are going to be the average of my neighbors, and it works pretty well because you're able to remove a lot of noise in this way. However, as you're saying, if you keep doing this for too long, and for getting influence from neighbors which are very far away, so if you have too many of these aggregations and averaging, at the end you basically collapse to a situation where pretty much all nodes have very similar features which are not kind of indicative of the nodes anymore. So basically it's there have been a lot of papers showing that if you take a GCN model, in most data sets 2-3 layers works the best, and then as you keep adding layers, the performance drastically collapse to kind of a random guess almost. So yeah, I think there is a trade-off that you really want to smooth the signal over the graph, because this is what removes the noise that individual nodes may have. But as you smooth too much, then you kind of lose also the signal.
So what I really liked about your paper was it just got me thinking about operators and the choices that a practitioner might have at their disposal, and really thinking about the graph that they're working with, and perhaps designing an operator that would suit it well. So basically your solution to this problem of not wanting to stack a bunch of layers and in general scalability is that you pre-compute the result of these operators on the node features, and then you cache them somewhere and look them up as needed. But since you don't have multiple layers, you don't have to keep re-querying the graph, right? So within the paper, you talk about a convolution-like operator and a diffusion operator. So can you define that and tell us why those are the operators that you're focused on here? What do you mean by a convolution-like operator?
So in this context, I think convolution and diffusion are used interchangeably. So convolution-like operator it's basically any operator that it's taking as GNN were kind of emerge from a way to define convolution on graphs similarly to how we define on images, right? So on images, convolution has many interpretations, but the one that probably was most useful to then move it to graph neural networks was seeing it as a weighted average of your neighbors. So if you think about each pixel, so convolution in images, you have this kernel which slides over the image, right? And the value after the value after the convolution of the central pixel, it's basically going to be an average of the adjacent pixels weighted by the convolution kernel, right? And this is basically also what we do on graphs. So on graphs, the new feature for a given node will be some sort of weighted average of the features of the neighbors. So basically, when you think about so these convolution operators are just operators that tell you, who are my neighbors and what are the weights. So it's basically it's some sort of adjacency matrix, right? But it also has these nice links to convolution, I think.
And how do these operators help us capture these more sophisticated features without needing to stack layers?
Right. So, I mean, so what we were given as input is usually it's like the adjacency matrix, right? So this is the graph we have, but then from the adjacency matrix we need to kind of choose how are we gonna use this to then aggregate information in our GNN. So the first approach is, so if you take GCN from Thomas Kiff, basically they have a normalized version of the adjacency matrix where you kind of the weight of a given neighbor depends on is basically 1 over the square root of its degree and your degree. So basically it mainly depends on the degree of the neighbor. And this, in practice, this works very well. But then clearly, this is a bit arbitrary. So for instance, if you take graph attention network, the idea there is actually, look, why should we kind of guess these weights? I mean, not guessing, but why should we fix these weights? Why can we just learn these weights? So this is what graph attention network does. In our case, so if you take sine, we can't do attention because this is done as a pre-processing step. So it's not something we can learn and have weights, which you need for attention. But to have a more general approach, what we want to do is not to just be kind of stuck with the original adjacency matrix, but also design other operators which may be more interesting in other scenarios. So if you take, for instance, the personalized page rank operator, which basically is just running personalized page rank. So for each node, the way you do it is basically the same as from each node running random walks and seeing how often am I gonna end up in another node, right? So this, you may have a node in the 2-op, in your 2-op. So in your adjacency matrix, you will not be connected to that node. But actually, if you start having random walks on the graph from a given node, you realize that you end up very, very often into this other node, which is in the 2-op. So it probably turns out that node in the 2-op is very important to this starting node, right? And then by seeing these frequencies with which we end up into nodes, we can then define another diffusion operators where now my kind of is like a different adjacency matrix where now edges are have weights, which are kind of the probabilities with which I end up in these nodes, right? So it's kind of a richer operator in this sense, and yeah, depending on the application, there may be other interesting operators that we want to use. So, for instance, in social network and complex networks, there have been a lot of research in network science showing that motives and triangles are very important to make predictions. And a triangle, it's basically, you know, when there are three nodes which are all connected to each other. So then we can define this triangle operator, which is basically, you know, the position ij is just gonna say how often, you know, how many times are node I and node j appearing in a triangle together, right? And these turn out to be something that is kind of, in general, very hard to compute for, you know, this kind of information is very hard to extract from for a GNN. And there is a whole, you know, other section of research investigating, you know, how expressive are GNNs, you know, some papers showing that most GNNs, you know, they're not able to compute triangles. But in this case, we're saying, okay, we can kind of pre-define and pre-compute some of these fixed operators, which are fixed. So, you know, it's not as flexible as potentially, you know, a graph attention network, but they work well in practice for, you know, different kind of tasks. But most importantly, they are, you know, they are fixed, and so they can be computed very, very efficiently as a pre-processing step.
So basically, something like the adjacency matrix is, you know, the GCN is applying the adjacency matrix, right? Essentially, and averaging the neighbors. And then you're saying you could go further away by, for instance, squaring the adjacency matrix, which would give you 2 hops. And then there's these more sophisticated operators that look for particular motifs. So the triangle being how many, for instance, if it's in a friend graph, how many friends are shared between me and this other node, right? And then that's the count of triangles. Is that right? So you're sort of putting this bias and weighting the connection based on how many shared friends me and a different node might have.
Yeah, pretty much. So it's, let me think if it's exactly, so if it's me and you and how many shared friends we have, yeah, I think, yeah, that should be, yeah, it's basically, yeah, the number of triangles that 2 nodes appear together in, right? So if it's me and you, and then, so maybe there is an edge between us, but then there is a lot of other people that are, yeah, they are connected to both of us, right? So yeah, exactly. So yeah, assuming there is an edge between me and you, then we want to count how many other shared friends we have exactly.
Yeah, so you're sort of, oh, go ahead, I'm sorry.
No, yeah, I was saying this is it. And yeah, as you're saying, there are, yeah, two different kind of ideas. So one is having different operators. So not only the adjacency, but also possibly these triangles, personalized page rank, and so on. And the other idea is having powers of these operators. And, you know, interestingly, if you have an adjacency matrix and you take the square of this matrix, now it gives you basically information which is also 2 up away, right? So my row in the adjacency matrix now is also contained in the square of the adjacency matrix. It now also contain weights for nodes which are in the 2 up in my graph, right? And it also has meaningful weights in the sense that when you square the adjacency matrix, if you see the adjacency matrix, you can see it as a random, pretty much as a random walk matrix. So then when you square it, it's basically what is the probability, the scores that you have in your square adjacency matrix is pretty much what is the probability that I'm going to end up there in two steps. And but in general, if you think about GCN, right? GCN, it's you have this normalized adjacency matrix, and then which multiplies the features and also some weights, and then you apply nonlinearity. But and then you stack some layers. If you remove the nonlinearity, so if you have an identity there, then you can basically see that this model collapses to just having one single set of weights and one single, you have basically the adjacency matrix multiplied by the number of layers. So let's say, I don't know, K. And so basically your model is your adjacency matrix A to the power K times the feature X times the weights W. And this is basically the model of simplified graph convolution, right? Where they say,
Right.
what if we just remove all the nonlinearities? Well, they showed that it still works very well and it's super fast. And so also that was a very big inspiration from our paper, right? We just said, look, if you have to compute a to the k, why not also, and by the way you never compute a to the k explicitly because it's very, very expensive. What you do is you multiply a by x, and then you take this and you multiply it by a again, and you keep multiplying a, which is a sparse matrix, by this dense matrix, which is more efficient. So what we just said, what we thought is, since you already do this computation, why not keep also all the intermediary results? So not just ak to the x, but also why don't we keep ak minus 1 to the x, ak minus 2 to the x, and also and starting from, and this basically brings us to thinking of concatenating just x, which would be, the identity operator times the features, but it's basically just the features. And then, ax, which is one, the normalization matrix, and then different powers, which is same complexity as simplified graph convolution, but you have more operators, which, arguably gives you a bit more expressivity. And then we can do this trick also for other operators, which is the kind of the topic we just discussed before.
So if I understand it, you basically say, hey, I have this handful of operators, 5, let's say, and some might be powers of the adjacency matrix, some might be other things, but I pre-compute them on the features of the nodes, and then I concatenate everything together, and I do a logistic regression on top of that, and I'm done. Is that basically it?
Pretty much. What you may actually want to do is not just a logistic regression. You may want to have something deeper, so an MLP with some layers, just because you want to have that expressivity that depending on your features may not be linearly separable, right? So you may want to have some layers after that, but it would just be an MLP, right? It's not, still you don't have the graph, so it's basically few fully connected layers. And in practice we see in many data sets that having 3-4 layers instead of having one layer of just MLP, so is unrelated to the how far you look in the graph. So just the MLP having 3-4 layers works much better than just having 1 or 2 layers.
So how do you actually find the right operators for your problem? Is this just basically another hyperparameter to search over, or is there some more kind of networky science fundamental way to go about analyzing your graph and saying, oh, well, maybe I see this attribute of my graph, so I should explore this type of operator?
Yeah, that's a very good question. So at this moment, I think, there is no kind of easy way. I think it's kind of domain specific. So, in network science, there is all this literature on complex networks and social networks saying that, triangles and cliques and these kind of motifs are very important. And so you can have a guess that these would be good operators, right? If you work with chemical data, with molecules and so on, I guess you're gonna need to think about that specific domain and think about some operators. But in general, you can kind of try a bunch of them and see what works. But I guess, knowing your domain and maybe seeing what kind of the more traditional network science literature has done is a good way.
So I've been working on fraud detection problems, and I'm wondering how this would work in the context of an evolving graph, right? Because the things I'm wanting to evaluate are kind of new nodes to the graph. And I know you have a whole line of work on temporal graph networks, which explicitly is handling these dynamic graphs. But in this case, where you're trying to put a sign-based model into production, is there a way to kind of update these operators in an offline batch job without recomputing them from scratch? or is it really that if you add a new node into the graph, you need to recompute all of the operators and then feed that in at prediction time?
Yeah, this is a good point. So this is kind of probably maybe one of the weaknesses of the method as it stands. You can think of, heuristics that you could use, but I think in general, you would need to recompute the operators. So for something which is it works very well if you say, I want to have a weekly weekly update. So you just have to recompute these things weekly, no problem, because your computation is, you can probably also daily, because your computation is not gonna take that long because you can distribute it and so on. If you need things real time, then yes, probably it's a bit of a drawback of the method. I think, you can come up with heuristics. So you can say, okay, I have a new node that I didn't have before. Certainly, you can have the adjacency matrix for that node. So basically, but it wouldn't be, very easily incorporated into the methods. I think you can think of some hacks, but yeah, the method is not very suitable for this kind of applications, unfortunately.
Yeah, I didn't know if there would be kind of simple incrementing updates that you could do to these values, that maybe someone's worked out the math on that, but it sounds like if there is those simple equations, it's not sort of easy to find.
Yeah, the issue is that you would need to, in theory, if you just add a node, or adding a node is even a more complex case, right? Because you need to add a row and a column to all the matrices. But even, if you want to think about the simpler case, even, you have a new edge. If you just have a new edge, these can change all the matrices in potentially in a lot of places, right? Not one entry in the matrix, but potentially it can affect, especially for higher order operator, right, which you look for in the graph, this can have an effect which is very far away. Then what you could say is, you can say, of course, an edge, maybe, I can approximate it to only recompute maybe, the score from for the nodes that it connect, or maybe the neighbors, because, the effect that is going to have on the far away in the graph is going to be very, very small. So I can approximate it to 0. Or you could even say, look, it's just one edge. So the edge, you can even ignore it, because it's not going to make a huge difference, depending on the task, right? If you have a new node, then it's more complex, because it's, you could say, what you could do is, if you have a new node, you say, okay, I'm going to just compute the operators, but only for this node. So I'm going to keep the operator for all other nodes fixed, which is an approximation, is not correct, because this node is also going to influence their operators. But I will just kind of compute the new row for this node. But also, it's probably not super efficient, because if you want to compute the power of its adjacency vector, you still need to multiply by the adjacency matrix. So it's kind of an expensive procedure, let's say.
So how do you solve this in temporal graph networks, where you're explicitly designing a mechanism for handling these evolving graphs that are adding nodes and edges and stuff? How do you handle that with the various matrices involved?
Yeah, so what we do there is I think the difference is that we don't really have pre-computation. So it's more similar to like a standard GNN with kind of sampling if needed, which I think it's important to have your model really inductive in the sense that it's able to handle new nodes. And so basically there, what you can do is, if a new node comes, in TGN, we have this kind of memory vector, which is just kind of a summary of the history of a given node so far. So basically, it summarizes all the interactions that the node had in the past. So if a new node comes, we just have to create one more memory and we initialize it to 0, and then we're just gonna do when we do our GNN to compute the embedding of this node, we just do it on similarly to I was introducing Graph Sage, we do it on the fly. So we kind of sample the neighborhood of this node. So if this new node appeared, then let's say it created 3 4 edges. So now it has 3 4 edges to nodes that were already in our graph. Then we can just sample this new neighborhood. So we sample this node that we want to make a prediction on. We take its neighbors, the neighbors of the neighbors, and then we can just have this let's say this tree, and we run our GNN on it and make a prediction on the original node. So it has this inductive capability because the convolution is done on the fly, very similarly to the Graph Sage paper.
Got it. That makes sense. So,
of course, with also with also taking care of the time. So time is an important component in knowing how to weight your neighbors and how to update your memory, which is what makes it different from what makes it temporal.
Right, and we should point out you have given some talks on this that are available. So if the people are interested in digging deeper into temporal graph networks, there's plenty of good stuff out there. So what is occupying most of your time these days? Is it the temporal graph networks, or is it a new line of work, or what are you focused on?
Yeah, actually, right now I would say my focus is mainly on working on temporal graphs. So I think it's a very exciting moment, but also it's kind of very early days, and there is still a lot of things that needs to be figured out. So for instance, there is a kind of a very big lack of data sets, of good benchmarks, I think, especially for different tasks. So the data sets that there are quite specific for specific tasks and also kind of specific scenarios. So it would be nice to have a bigger variety of data sets which are large, which are hard. And I think we're not there yet. So I'm kind of also looking into trying to create some more data sets. And but in general, yeah, I think there are so many problems which can be seen as temporal graphs, and I'm kind of trying to focus on this direction now.
So where do you think GNNs are going to be having the most impact in the next 5 years or so, based on your experience and seeing kind of the landscape of problems at a place like Twitter? Where do you see them having just a ton of success?
Yeah, I think in 5 years, they're gonna have a lot of success for sure in industry, in recommendation, and in finding, for instance, bad actors on platforms, so spam, abuse, this kind of things. I think GNNs are very well suited to that. I think they are also going to have a big impact in kind of chemistry / biology, so working with molecules, so drug design or drug repurposing. That stuff I haven't really worked directly on a lot, but I always find interesting reading about. Michael also has done is doing some work on this, and yeah, I think there could be it's a very natural tool to model. If you have a molecule, it looks pretty natural to model it using a GNN, and there starts being a lot of data. And the problem are very, very important, right? So if you can find new drugs in a much faster time span than it was done before, I think that can have a huge impact on society.
Yeah, for sure. So my experience is somewhat similar to yours. That I'm at AWS and have worked on fraud, but they're probably similar in terms of scale, although yours is, I'm sure, larger. But I see dynamic graphs as being kind of the norm in these industrial applications, at least for things like fraud detection and fake news and all that stuff. And I also see how scalability is really important. I'm wondering if there's other fundamental challenges aside from the dynamic and scalable features that you think are kind of a challenge to this wider adoption.
You mean for, in particular for applications?
Yeah, like what would stop a company, for instance, from putting a GNN in production if we ignore for a moment the questions of scalability and handling dynamic graphs? Are there any other fundamental issues that need to be addressed, or are those kind of the two big ones?
Yeah, I think as I was mentioning at the start, I think the infrastructure can be tough because probably, if you want to deploy a GNN, Python geometric is not going to be enough, even though it's an incredible tool for research. But for if you want to do deployment, you need a whole different set of frameworks, right, which are focused on that.
So you mean things like to do the neighborhood sampling and to traverse the graph?
Exactly. Yes. Okay.
So like
exactly
inference
to do. Yeah, I mean it's a whole thing of basically going from data which is is not in a CSV, is not on your machine, but it's in some distributed storage. How do you go from there to doing the right sampling and to having the right data in your GPU machine? I think that's still kind of as far as I know, there are not any open source tools for this yet. So companies clearly have implemented their own, but as I think for really widespread adoption, having something like for instance TensorFlow made it very easy to deploy machine learning models, right? I think since graphs have some additional complexities, I don't think there is an equivalent for graphs yet, which is widely available and open source and everything.
Yeah, I've used DGL, which is part of AWS. There's a service team that manages the DGL, and I know they released a distributed version of that, but I'm not familiar enough with it to say whether it solves these sorts of scale problems. But it seems like progress is being made, but I don't know. Whoops, sorry.
Yeah, no, I'm sure people are working on this. So I don't see it as a blocker, for the next 5 years. But I would say right now this is probably one, a point which is still a bit painful. So great. I would say the tools for doing research on GNNs now are like just incredible because whether you use Python geometric or use DGL, you can really do great research with the ability of focusing on your question, your research question, your problem, and without worrying about all other data loading or model implementing all the models from scratch. You can literally change one line and have a completely different model and have a completely different data set and so on, which is great. And it didn't used to be like that 2-3 years ago. And I think we're not at that point for industrial applications yet for deployment.
Let's see. So I remember reviewing a blog post from Uber Eats, and I talked to one of their scientists there that they had a post about deploying GraphSage in a product recommendation setting. And they did something where it was kind of like a hybrid real time where they'd run these offline batch processes to update node embeddings, which they would then cache and then serve in like a real time setting to like a traditional model, like a tree-based model, and just use the graph methods as kind of a feature extractor. Have you seen things like that operating at scale, or are you actually seeing inference being done where, as we were describing before, you have to kind of query the graph and gather the neighbors and do that in real time.
Yeah, I mean, I read the Uber Eats post, and yeah, I mean, this is pretty much what I mean. Like everybody has to kind of find their own solution, right? Because there is no kind of widely agreed and available solution. So I think, I mean, this is a solution, but probably the more ideal solution that you want is to have also at inference time a way to sample the neighborhood of nodes and and do a full GNN on the nodes. That I guess that's the end goal. And if I remember correctly, at the nearest workshop, there were a few talks by Google, which also discussed their infrastructure for doing this, and I think they was pretty interesting. So yeah, they had something internal which was working quite well for this.
Yeah, I'm also seeing my bias is towards AWS services since I work there, but there's a Neptune is their graph database service, and then there's Neptune ML, which has these DGL models sort of ingrained into the service as like a function call. So you can just kind of like your SQL statement of select average of this column, but it would be select the model of this node, and it would sort of evaluate it as part of the graph database, which I thought was a kind of a clever solution.
Yeah, I mean, that's very cool. Yeah, that's very cool. It's not something I saw before, to be honest.
Yeah, it's pretty new. I think they just announced it a couple months ago. But anyway, what are the research groups that you follow that get inspiration from, or you just think are doing kind of exciting work right now?
Yeah, I mean, of course, Jure Leskovich, Stanford. They have a lot of very good people, a lot of very interesting research, and also they kind of started the Open Graph benchmark, which I think it's super important for research on graph neural networks. That's one. I mean, there are so many. There is, I think, Javier Bresson in Singapore is also doing very interesting work, and he also gave some great lectures. I think it was for the course from NYU. One on more basic fun things and one on recent developments, which I found super interesting. But he's also doing some interesting work on combinatorial optimization. I saw they just organized a workshop in the coming months at UCLA. The group in Munich, in Munich TUM of Stefan Gunnemann. They also do super interesting work. Some on adversarial attacks, which I never worked directly on, but also some on they had this paper I liked very much about benchmarking GNNs, which at the time was something not done very often, but was kind of showing that when evaluated fairly, most of them perform very similarly in GCN, which was very simple compared to all the models developed later, was kind of performing the best very often.
Even label propagation.
So, sorry?
Is that the ones that showed that even kind of the simple label propagation worked as well or better than GNNs on most of the open data sets?
I think there was a more recent ones, right? And they got the leaderboard on most of OGB on OGB data sets. That was also a very interesting paper. But no, the one I refer to is a bit older, probably two years plus ago, just purely about benchmarking. But also label propagation was very interesting. I also follow Petter, which is also a good friend. I still have to watch the talk he gave a couple of days ago in Cambridge, which was I saw it was very well received, so I'm looking forward to it. And yeah, but I mean, yeah, there are others as well, which I mean, there are research coming out of so many places, and I mean, of course, a lot of things from in general from DeepMind clearly.
Sure.
Also, yeah, Battaglia there is doing some interesting work with GNNs on physics, right?
Yeah, for sure. I got to talk to one of them about their particle physics simulators from graph networks. It was really cool. But the other thing that strikes me is how a lot of the people you're talking about are putting content out there and talking to people like me and just letting the broader community hear their insights. And I think that's super cool. And one of the things I've noticed was the blog series that Michael Bronstein has put out. And I know you've written some of those and have one out on the Temporal Graph Network. So that's just super cool. Thank you guys for doing that. Where else can people find you and get content, or I don't know if you tweet a lot, or what do you have out there on the internet that people can follow?
Yeah, I'm, let's say, reasonably active on Twitter. Maybe not daily or weekly, but bi-weekly, let's say. And I also have a website where I have some of the slides of my past presentations, and couple of more things about myself, which is just my name and my surname.co.uk. And yes, I would say that's pretty much it.
Cool. I'll put a link in the description, of course. Well, stick around for a second. I'll wrap up the recording, but I wanted to pick your brain on one more thing. So thank you so much for taking the time out of your day. It's already been an hour. It flew by for me. And
thank you. No, it was great.